In Math 107, as far as series and sequences are concerned, we generally study the arithmetic and the geometric sequences and series. In an arithmetic sequence, the difference between adjacent terms is always the same. Here's an example of an arithmetic sequence. If you subtracted any two adjacent terms, 9 and 4, 14 and 9, 29 and 24, you always get 5. That's called the common difference. In this case, the common difference between terms is 5. The recursive definition for this particular sequence would give you a starting point of 4, and then, I have to write this out, the term you want to compute would equal the previous term plus 5. For example, if you wanted the 6th term, that would be the 5th term, and then add 5 to it. Here it is in general. For arithmetic sequence only, A1 is just the beginning term, as it always is. Then AN, the term you want to compute, equals the previous term, AN minus 1, plus that common difference of D. If you think about the sequence again, we have 4, 9, 14, 19. Okay, if you think about this, it's true that each adjacent term, the two adjacent terms are different by 5. But you can think that this term is really the starting term with however many 5s added onto it. To get out to here, you don't have to leapfrog your way all the way up to 24. You can start at the first one and just add 4 to get to the 5th term. Okay, 4 of these common differences, in this case 5. And that's how you can wrap that recursive definition for an arithmetic sequence into one line. And here it is right here. You'll see the A1 is embedded in it. What this says is the term I want to compute, say a to the n, equals the first one plus however many common differences added in. You don't have to specify the first one, because if you let n equal 1, then I would have a1, but now I have n minus 1, which is 1 minus 1 times d, so I just get a1, so it starts out okay. Then look at the 5th term. 5th term would be the first one plus 5 minus 1 times d, so that would be the first term plus 4 common differences added in. And that's a shorthand way of wrapping that recursive definition into one line. Now here's a geometric sequence. In the geometric sequence, it is not the difference that's the same, it's the ratio that is the same between adjacent or consecutive terms, and that's called the common ratio. Here's an example. If we take 6 divided by 2, we get 3. 18 divided by 6, we get 3. 54 divided by 18, we get 3. The 3 is the common ratio. Another way to think of this is that the 18 is 3 times 6, the 54 is 3 times 18, 6 is 3 times 2, and that's how you write the recursive definition. So here is the one with 2 steps. Specify the starting point of 2, then say that the term you want to compute, a to the n, in this case is 3 times the previous one. So a to the 6th would be 3 times a to the 5th. Just like the arithmetic sequence, the geometric sequence can be written in one line. And here it is right here. And I'll show you for this particular one. What it means is that instead of, again, leapfrogging up, 2 times 3 is 6, 6 times 3 is 18, 3 times 18 is 54. You can instead start with the 2 and just multiply the 2 by as many 3's as you need to get up to 54. And that would be done by using an exponent. So I could say a to the 4th is equal to the first term times that common difference, in this case, or the common ratio 3, raised to the n minus 1 power. That will give you all the terms of that geometric sequence. So now we'll move to the series, and remember we have all these words starting with S. Set is just a group of items, we'll say group of numbers, no order. sequence has order. It's an ordered list. The series is the sum of the terms of the sequence, where they're all added together, and all these start with S, and that's a confusion, but I think you can see it here. Now for this class we're only going to look at the arithmetic series and the geometric series because they have very handy formulas. And here's a handy formula. Let's say I want to add up n terms, like the first 153 terms of any arithmetic sequence. Any arithmetic sequence. That's a sequence with a common difference between the terms. Here's the sum, the notation, but that has this handy formula. The number of terms I want to sum up I put here. Then I add, multiply that by the first term plus the last term and divide by 2. So if I had, here's my arithmetic sequence. The common difference is D is 2 because it's 2 between adjacent terms. And let's say I want to add, how many have I got here? 6. So I want to add 6. Well, I could just brute force add them up. 2 plus 4 plus 6 plus 8 plus 10 plus 12. Or I can use this formula. So the sum of the first 6 terms equals the number I want to sum, which is 6. The first one, which is 2. The last term that I want to add up, which is 12. And divide by 2. Obviously that's a lot easier, and that's what's said in the second line here in words. Let me show you where this comes from. It's a very famous calculation. This calculation is attributed to Gauss, who was a very famous mathematician, and he supposedly did this at the age of, it changes, I think, 5, 3, 2, I don't know, at a young age. The idea was that he was supposed to add up, or the class was given the assignment to add up the first 100 numbers. Perhaps the teacher had something else to do and needed to keep them busy. But here's what Gauss did. He noticed that you could add these in one direction. In this case, let's just do 2, 6, 10, 14, 18 instead of 1, 2, 3, 4, 5, but we could do it that too. This is an arithmetic sequence with a common difference here of 4. You could add them in this direction, as you were told to do, and you get one answer. You could also add them the other way, 18, 14, 10, 6, and 2, because addition is commutative. Right? So you can add them 2 ways and you would get the same sum. The upgoing one or the downgoing one would be exactly the same. Now let's add these 2 together. 2 and 18 is 20. 6 and 14 is 20. 10 and 10 is 20. You always get the same. That's, a property of this arithmetic sequence. 14 and 16 is 20. 18 and 2 again is 20. How many 20s do you have? You've got 5 of them. These are the same, and they both equal the sum. So the sum of the first 5 terms you'd have twice. You would have done it twice. Equals the up or down equals 5, the number I wanted to add, times, and the easiest way to get this 20 is to add the first and the last. You could do something in the middle, but the first and the last are most readily available. And then, well, I have 2 of them, so I divide by 2. Right, and that's the calculation that leads to the sum of n terms of an arithmetic sequence equals the number of terms you want to add, the first term you want to add, the last term you want to add in your group, divided by 2. Now you might think this is just sort of esoteric, but here's an application for it. Say you have logs piled up and you want to know how many logs are in the pile. Okay, let's say the bottom layer has 48 and each layer has 1 less than the other one until you get to the top that just has 1 log in it. Now how could you find out how many are in there? You could add 48 plus 47 plus 46 plus 40, etc. You could do that, or you could recognize this is an arithmetic sequence. The difference between each row is 1. The first term, well, I'll start with 1. You could start with 48, and the common difference here is 1. You could start with 48 and say the common difference is minus 1, but let's just do it like this. Okay. Now, how many logs are in the pile? Here's the formula. how many rows are there? There's 48 rows, so I'm trying to add 48 rows of this arithmetic sequence. So I put the 48 here according to the formula. The first one I want to add is where you can put the 48 and the 1, doesn't matter the order here, of course, and then divide by 2, and I get 1176. It's a lot easier to calculate them this way than to try to add them, even if you use a calculator, because you could make a mistake in inputting the number. Sometimes your arithmetic sequence doesn't start with 1, or you're starting in a different place in the pile of logs. You can still use the same formula. Let's say the top layer had 12. Well, let's say we started with the one that had 48. So it's got 48 in the bottom row. And instead of going all the way to 1, the top layer only has 12 instead of 1. The problem here is it's going to take a little bit of work to figure out how many layers you have. Remember the fence post problem when we were counting with the segment notation. To find how many layers you have, because you're including the layer with the 12 in it, would be 48 minus 12 plus 1, which is 37. You might just have to count on your fingers to figure out how many layers you have. If on the test or the homework you make an effort to find out how many layers you have and you don't come up with the right number, but you make an effort and you show what you did, I'll probably give you quite a bit of credit for that. So here's the answer right here. You want to add, you end up knowing you want to do 37 layers. The first layer you want to add has 12. The last layer you want to add has 48 in it. You divide by 2, and there's your answer. This works even if the common difference isn't 1. If the common difference is 10 or 20, it still works. For a geometric sequence, the sum of the geometric sequence also has a formula. Here's a formula here. If anyone going into business will see this formula or variations of it when you start working with annuities. Its derivation is similar but not identical to that for the arithmetic sequence. Let's say I have, I want to add up in terms. So I'm going to call this, I'll just call it S. The first term is A1. The second term would be A1 times the common ratio R. The second term would be A1 times R squared. The next term, let's just go this far, is R cubed. Okay, and I want to add 1, 2, 3, 4 terms. Now, with the arithmetic sequence, you just turned and added them backwards to get the formula. Here, I'm going to multiply this by the common ratio R. So R times S to the 4th. So I'm going to offset these. It will look strange for a minute. So I multiply this whole thing by R. So I've got the R turns to the R. What happened? Oh, that works. Okay. If I'm offset them, but if I multiply this by R, A1 times R would give me this term. A1 times R multiplied by R gives me the R squared term. You see they're offset. I just multiplied the whole thing by R. The reason I did this is because now I want to subtract. So I'm going to subtract these two rows. Subtracting, I get the A1. But these subtract off, these subtract off, these subtract off, and the only thing I'm left with is A1 times R to the 4th. So I have S to the 4th minus R S to the 4th equals A1 minus A1 times R to the 4th. So factor out what you can. I get S to the 4th factored out, leaving me 1 minus R. And here you could factor out the A1, but alright, I'll do it. A1 times 1 minus R to the 4th. Then if you want S to the 4th, you divide A1 times 1 minus R to the 4th divided by 1 minus R, and there's your formula for the sum of a geometric sequence. This is the geometric series.